Yeah, hello everybody and welcome to the next lecture in Bioprocess Engineering. So don't worry, we are in Bioprocess Engineering. Obviously I've forgotten to change the jingle. I thought I did it, but obviously I didn't. Okay, today you have no lecture, but there is a lecture because instead of uploading it simply, I just decided do it live so you can choose whether to follow or not. Okay, so we will start right away with the example and your homework which you have uploaded.
All examples in this section are based on the Bioprocess Engineering Principles, second edition, Academic Press from Pauline Doran. The solution path is also depicted in this book, so please refer to this book for details, and it's again a warm recommendation to have a look in this book.
This is the example. The example is that we manufactured citric acid using aspergillus. The batch reactors operated 30 degrees over a period of 2 days. We produced 2,500. We consumed 2,500 glucose and 860 kilogram oxygen, and produce this of citric acid and so on. Ammonia is used as nitrogen source. Obviously, if we look at this, it's 2,000 kilogram which come out, 3,360 kilograms which get in. It's not balanced, obviously, this system. Ammonia is used as a nitrogen source. Power input to the system is about 15 kilowatts, and approximately 100 kilograms of water is evaporated. So this is what you have here, and the first thing to do is, of course, setting up a flow sheet, and we have already discussed that last week. So this is how the flow sheet looks like. You have your glucose ammonia coming in, citric acid and so on coming out, and we have our agitator, and we have our water vapor getting out and our oxygen getting in, and of course we want to know the cooling requirements. We already discussed that we don't add the water which is the solute here, which usually had to be done. But as we neglect sensible heat, and this you have to put in your assumption that we neglect sensible heat, we don't use the water in this approach here. So the water which is not the reaction water. The reaction water, of course, could be something which is relevant. So here you need to set up the reaction equation, and you will see that, of course, carbon dioxide is being produced, and of course also water is being produced. So this can come out from the reaction. However, now the first question to ask before starting is, it's an aerobic process. What is the energy balance which is appropriate? The energy balance we use is this one. Because we neglect sensible heat changes, we only look at the heat of the reaction, we only look at latent heat, we only look at the heat, of course, what is leaving or has to be put into the system, and we only look at shaft work. And these things are given. So we know the shaft work, that's what we want to calculate. We can calculate the latent heat because we know how much water is being evaporated, and we have the value directly. And we need to calculate the heat of reaction. For calculating the heat of reaction, we have two ways to do that. We can, on the one hand, use the heats of combustion, and then we just need to subtract reactants, the sum of the reactants and the sum of the products. So this is what is one possibility. Then, of course, we need to know the masses of all components. The easier way is, if it's an aerobic process, just calculate the heat of reaction based on the oxygen consumed. And now comes the good news. We have the value for the oxygen consumed here, and it is an aerobic process. So the cool thing is, we don't need to complete the mass balance here because we have the oxygen. And then the things get very simple, because at the end we just need to put in this oxygen consumption in the equation, and that's it. So let's just solve it, and you will see that it's just, in principle, it's just 3 lines, and that's it. Yeah. What we said is that we simply want to use this energy balance, minus delta HRXN minus the latent heat minus the heat leaving the system, shaft work is equal to 0. So that's our energy balance. And as delta HRXN related to oxygen consumption, and therefore it's very simple. It's delta HRXN is equal to minus, this is the equation you have in your formulary, minus 460 kilojoules per mole, volt, your 860 kilograms, volt. Now you have to convert it. We need to convert it into grams because we have our molar weight is always in grams. So we need to get the kilograms in grams. We do 1000 gram divided by kilogram. This kicks out our kilogram. Volt. The molar mass, we need to get the grams out here. So it's 32 grams per mole. And therefore it's equal to, you put that in your pocket calculator, and then you should come out with 1.24 times 10 to the 7 kilojoules. So that's my heat of reaction. So I have already this value. Done. The next, what I calculate is my latent heat. So my latent heat is simply mV delta HV is equal to, I have 1000 kilogram. And now I go to the steam tables where the latent heat is listed. I need to know the latent heat at 30 degrees. And this is simply listed at the steam table. So I'll look it up. So you have this table there. And if you look in your table, you see it's 2430.7 kilojoule per kilogram. Our kilogram leaves, and then I end up with 2.43 times 10 to the 5 kilojoule. And this goes in here. Okay, the next what we do is we go for the shaft work. And the shaft work is, we have a power input of mechanical agitation is 15 kilowatts, which is the same as 15 kilojoules per second over a period of 2 days. So 15 kilojoules per second. This is the power of my mechanical agitation. Fold 2 days. And now I need to convert the days into seconds. And this is, of course, very simple. 1 day has 24 hours. Per day. So the day is gone. Fold, of course. The day, we make it the S, we make the S leave, then we can shorten out the day without having an S left. And then we need to convert the hours into seconds. 600 seconds is 1 hour. And then we end up, if we put this in a calculator, we end up with 2.59 times 10 to the 6 kilojoule. So you see that we have to take care of all these values because all of these values are at least in the same order of magnitude. You see that this value is 50-fold higher than this value, but nevertheless, we need to take that into account. So now we put everything in this equation and we solve it to Q, and then we simply will get Q is equal to 1.47 times 10 to the 7 kilojoule. And that's it. So you see, it's really this simple as promised. So I will have a look in the chat whether there are questions which have coming up. Yeah, for the latent heat, it's 100 kilogram, not 1000 kilogram. Did I put 1000 kilogram? Yes, I put 1000 kilogram. This is of course wrong. It should be 100 kilogram. So it's 100 kilogram because it's the water leaving the system. Sorry, my error. Yeah, I'm not so sure. Honestly, I'm also a bit surprised with my flow sheet value. I'm not so sure whether this flow sheet value is correct. I need to double check this. Yeah, the MB should be 100 kilogram, of course. So this is what we have changed now. So this is in very brief the homework. So that's it. Yeah. So now let's come back to the presentation. So that's our energy balance. This is now what we have calculated. And unsteady state mass balances, we don't talk at this point because we will talk about that when we come to kinetics. So that's it for mass balances. And therefore we can go now to the next chapter. So we will talk about mass transfer in bioprocesses, and at the end we mainly will talk about oxygen transfer, because you will see that the problem number one in bioprocesses is bring the oxygen into the liquid. Okay, you should know about typical mass transfer contributions, how mass transfers at phase boundaries are calculated, and know how the oxygen transfer is defined. Okay, let's start with mass transfer in general. Okay, so we now first have a look, if we talk about mass transfer in fermentation, we first have a look what transfer processes are there. So what type of transfers do we have? So we have three general types of transfers, and that's what you know already from thermodynamics. We have mass transfer, we have heat transfer, and we have momentum transfer. Mass transfer is, for example, the transport of nutrients from solid particles via the fermentation broth to the microorganisms. Very simple. Heat transfer, we have talked about that in energy balances. This is taking out the heat of the system, for example. And momentum transfer is, of course, also something we're talking about. If we have a stir in our system, the energy needs to be transferred from the stir to the broth. So this is momentum transfer. So all three basic transfer processes are relevant in fermentation. Now, in this lecture, we will mainly talk about mass transfer. Heat transfer, momentum transfer will not be looked at. The good news is the general way to treat or to look at these transfer processes is similar, because at the end it's always a driving force. A constant gives you the mass transfer, and the mass transfer is described by Fick's law of diffusion. The heat transfer is described by Fourier's law of heat induction, and the momentum transfer by Newton's law of viscosity. And you see that the look of this equation is in all three cases similar. Of course, you can make it more ugly. So if you are in 3 dimensions and want to talk about momentum transfer, then we are no more here. Then things are getting more difficult and more problematic. Nobody understands it, with the exception of Frank Blatte. So if you want to if you want to go deeper in momentum transfer, talk to Frank Blatte. He will be very happy. So mass transfer, we have 2 basic types of mass transfer. We talk about diffusion and we talk about connective mass transfer. So when we have diffusion, just means that convective means that I push my particles with another force through the system. So I have a wind, and due to this wind, my oxygen particle is transferred from here to here. If there is nothing which pushes it, it's just by spontaneous diffusion. So when I have, for me, the speed of mass transfer is of course the interesting thing. So when I have both types of transfer, the speed of transfer usually compares as follow. Very simple, that the connective mass transfer is way faster than the diffusive mass transfer. And so in other words, if I look for mass transfers in areas where we have both, when I have a particle going through, you see that overall, hopefully you have seen it, hopefully you have seen it, that in the diffusion part, the particle stays the longest time. So the diffusion is the rate limiting step. So in other words, if I want to look at transport processes and I have diffusion and convection, then it's enough to look at diffusion with respect to calculating the overall transfer rate. This is cool because this makes our life simpler, because I don't have to do both. At the end, what are we talking about? We talk about this is now liquid, where we have a substance with a concentration C1 on the left hand side, and we have on the right hand side we have a concentration C2, and in between there is a phase border. So if we look at this system, obviously there is a gradient of the concentration at the phase border, and we want to know the transfer of the masses from the left side to the right side. It's clear that we have a transfer from a higher concentration to the lower concentration. And now, if we look at the concentration gradient, it looks like this. So it's a steep gradient here because we have a phase border. Now, of course, the question is, how high is our mass transfer? So the rate of the mass transfer must be proportional to a driving force. The driving force is the concentration gradient. So obviously the higher this concentration gradient is, the higher the driving force. And another thing is, the higher this area is, the higher also the transfer. And therefore at the end, you come to a very simple equation where you have the mass transfer rate is equal to the transfer area, fold the concentration difference, fold a constant. And this is your mass transfer rate. And if you want to calculate, now you have of course an area inside, the mass flux density is simply then without the area, the mass transfer coefficient, fold the concentration difference. That's it. Now this is if we have a phase border. What about if we have diffusion? So in this case, we have no phase border. We want to see what is the mass transfer from here to here. So we have already talked about it. Of course, also here, it's a gradient of the concentration is the relevant driving force. As here, we don't have a discrete gradient. We have a continuous gradient. Of course, the steepness of this curve here is the driving force. This is then simply depicted as dc dy, so it's the gradient over the y-axis. And again, I put a constant here, and this is my mass flux, and this is my binary diffusion coefficient of the substance I. This is my rate of the mass transfer, and I simply can calculate it like this then, with the mass transfer area. And this is again the flux density here. So this is at the end very simple, and this is what you have already talked about also in most likely thermodynamics. Now let's come to the role of diffusion in bioprocessing. So where do we see diffusion? So if we are talking about mixing or agitation, if we have our small lab scale bioreactor, usually diffusion is not a problem because I can put in so much power in my stir that I don't have areas in a usual fermentation broth. I don't have an area where I have only mass transfer via diffusion occurring. So my every molecule in my bioreactor is pushed by the stirrer, you can say. Across boundaries, however, I have diffusion. So I can have boundaries of phase changes: solid liquid, liquid liquid, gas liquid. Solid liquid is of course if I have solid nutrients in my bioreactor, which are hardly soluble, for example, and which is transferred, or if I have cell clumps in my bioreactor and then the solid needs to get into my cell clumps. This can be unintentional, these cell clumps, but I could also have bioreactors where I have immobilized cells, and of course then I have also a solid liquid transfer. I can have liquid liquid transfer. So if, for example, I have oil, I want to degrade oil in the bioreactor, or if I do a liquid liquid extraction of penicillin, even I can do this already during the process, and then I have a liquid liquid transfer. And of course I have gas liquid transfer, which are basically the oxygen transfer into the medium. So these are the mass transfer types I have. We will mainly talk about solid liquid transfer, we will talk about solid liquid transfer, and we will mainly talk about gas liquid transfers. Okay, so this is about a general thing about mass transfers across in bioprocesses. Now we come to mass transfer across boundaries. Now we look at these mass transfers more precisely. Now the basics of how we look at this mass transfer is the so-called two-film theory. So the point is, at the very beginning we had our scheme where we had an phase border. We had a concentration 1 here and a concentration 2 here. And we had a concentration gradient which was like this at the phase border. So this would mean that if I have a completely stirred system on the left side and a completely stirred system on the right side, for example, if I have two flasks which are separated by a membrane, I stir both flasks, so the concentration in these flasks is the same. So I will have just a difference at the phase border. However, if I go very close to this phase border, it's clear that there are forces on the surface of this phase border which doesn't allow, let's say, the stirrer power to get there. So it's like there is a film on the phase border, and this is the called two-film theory. So I will have a film on the phase border because the particles adhere kind of there at the phase borders, and the closer I am at the phase border, the stronger this is. So I consider the system then in this case as completely stirred and an even distribution of the concentration, but at the phase border I will have a certain film, and there I don't have convective mass transfer, I will have diffusion. And as I have no convection, there will be a concentration gradient. So this means that the concentration here, so I will have here the mass transfer from phase 2 to phase 1, by the way, if I depict it like that. I have an even concentration distribution in this phase because I mix, for example, at the phase boundary. I have a gradient due to diffusion because I have a film on the surface, and the same is true for the second phase where I have also complete stirring with a lower concentration, and I have then also a phase gradient here. And here directly at the phase boundary I have, let's say, a step, and this depends then on the system how this step looks like. We will talk about that. The concentration, of course, of the substance here is an equilibrium. That's clear, and it depends on how this equilibrium looks like. Depends on the system we are talking about. So this is the so-called two-film theory. It's a theory, yeah, but it helps then to mathematically approach the system. So that's the important thing, and most likely you have already talked about that, so you will not see too much new things here, and this makes life easy. So let's look at the solid-liquid transfer. I assume I have now a solid. This could be a solid where I have my nutrient, and this of course needs to get first into the liquid phase in order that my microorganism can metabolize it. You have to bring everything first in the liquid phase, even if the microorganism is not in a freely floating in water. On the surface of the microorganism you will always have a liquid phase where the transfer starts. So this liquid phase, this into liquid transfer, you will always need for microbial growth. So the point is, if you have a solid, in this case you have of course a solid with a quite low solubility, so you will have a certain concentration in the liquid, and you will have then a concentration gradient on the top of the solid-liquid interface. And you know that the driving force of the mass transfer is this concentration gradient of your concentration in the liquid, which you can measure, and this concentration on the solid-liquid interface. In between you have your film. Of course, in the solid you don't have a film because it's a solid, so that's the point. So this concentration here, how high is that? Well, that's very simple. At this point, you have an equilibrium between the solid and the liquid. And obviously, the concentration here must be the solubility of the substance in the liquid. So this is the saturation concentration, simply. And therefore, you have your driving force. It's simply the saturation concentration minus the concentration in the liquid. Then, of course, your surface of your solid-liquid interface and a transport coefficient. And this is then, at the end, the mass transfer rate here. So very simple and very straightforward. So we want to look at the gas-liquid oxygen transfer. Now, we have two phase borders. We have a phase border, which is the gas. So we have one phase border, but we have the gas phase. So we could assume that there is a film in the gas phase to the gas phase border, and we have a film which is on the part of the liquid side. And this then, in other words, yeah, this is what I said. And therefore, we have two, let's say, diffusion phases, here a phase and here a phase. And we can, for both, we can have a concentration gradient here, which is the partial pressure. In the gas phase, you talk about partial pressures. You have the, if it's 1 atmosphere and you have 21% oxygen, it's 0.21 atmospheres. It's a partial pressure of oxygen. So this is your oxygen concentration in the gas phase. Here it will be lower because it's taken out here. So we will have a concentration gradient, and then we will have a rate constant. The same is true, of course, in our liquid phase. I will have a certain concentration directly at this gradient here. We will talk in a second what the concentration is. And we will have a concentration in the liquid phase, and this is our driving force, and as again, of course, the constant for the liquid phase. Now, if we talk about the phase boundary here, the cool thing is that we have laws here, and we have the Henry's law. And the Henry's law says that the partial pressure in the gas is equal to the law constant for the saturation concentration. In other words, if you have a system which is in the equilibrium, this is what you know. If you measure if you have a liquid where you have gas in the liquid and allow it to go into equilibrium, then you will have a state where you have a certain concentration in your liquid and a certain concentration in the gas phase. And this is, of course, depending on the temperature and so on, that's clear. But this is then dictated by Henry's law, and this is what you know. So if you know Henry's law constant, you can calculate from your gas phase what is my saturation concentration in the liquid phase, because this comes from the equilibrium. And this is exactly, so this Pg is your Pg here, and this is exactly the saturation concentration at the liquid phase. This is cool. Now, the next question is, of course, we can now say the flux density, of course, then depends on this flux here at the gas phase in my diffusion phase and the flux in my liquid phase. However, again, we're engineers, so in principle, we would need to consider both. However, in a gas phase, you agree that this liquid film is certainly thinner than in the liquid phase, first of all. Second, the diffusion coefficients in gas are orders of magnitude higher than in the liquid phase. So this means that the rate here is way higher. It's diffusion in the gas happens way faster than in the liquid phase. So it's around the factor of 1000. So this means if you want to calculate the overall rate of the transfer from the gas phase to the liquid phase, it's enough just to look at the rate of the gas transfer here in the liquid phase, because this is not even a % difference in this case. And this is, of course, not relevant for such a system. So this means that for this transfer, we only need to look at this gas transfer here. And this is then at the end the equation we come up. So it's the flux density is the flux density here is our concentration difference. So the saturation concentration minus the concentration in the liquid. Of course, this concentration I can, using Henry's law, I can also write down like this. Fold, as always, a constant. So, and this of course depends on the liquid, this depends on the temperature and so on. So this constant is not constant if you vary the conditions in your liquid on the viscosity and whatsoever, but for a given medium, given condition, this is constant. Okay. Now, however, we know that the overall mass transfer, of course, also depends from the surface area. Yeah, so the higher the surface, the higher our mass transfer. That's what we have said at the very beginning. So let's have a look in how we take into account or how we put the surface area in our system. This is what we have already said before. In our fermenter with an aqueous phase, we have this transfer rate constant and the difference, and we have then just to take into account the surface area, and this gives our oxygen flux in a fermenter with aqueous phases. So this looks straightforward. However, you would say, what is this area? So if I have let's say if I have Erlenmeyer flask which is just standing there, and then have an aerobic process, it's easy. If it's shaking, then to calculate the surface is possible, but already more difficult. If it's rigorously shaking and I have baffles, calculating the surface is almost impossible. And the same is true if I sparge my bioreactors, because I have thousands of bubbles inside. It's merely impossible to accurately calculate, or even to reasonably calculate the surface. It makes no sense. So the problem is the surface I don't know. And this, of course, then makes my math, this breaks my neck with respect to the mass, because I don't know the surface. And of course, I can easily vary the surface with certain conditions, with certain variations. So I cannot do anything here if I don't know the surface. So what we will do to approach this problem is we define the oxygen transfer rate as such that we have an oxygen transfer rate where we take the surface in relation to the total volume of the liquid phase. So in order to make it comparable, so we divide that by the volume of the liquid phase, and then we have our gas liquid interfacial area per unit volume of fluid. It's a unhandy definition here. And then the complete KLA is our mass transfer coefficient. In other words, what we do at the end is we are aware that it's not possible to measure the surface, so we look at the complete term here, and that's what you do always. If you talk about oxygen mass transfer in your culture, you determine the complete coefficient here, the KL, and together with A, and you don't care at the end what is going to what, but as you know its surface and this constant, you of course know how to increase the transfer by increasing the complete term. So this is of course still important that it's surface and this constant. However, as you cannot measure it, you treat it mathematically as one figure, because you can't measure each individual issue. If I now in more practical terms look how things look like in cell culture. Oxygen, the solubility in oxygen is unfortunately rather low. So it's below 10 ppm at 25 degrees at 1 atmosphere. And this is my number one problem in cell culture or in fermentation, because if I cannot do it like with the other substance that I put everything at the beginning inside of my bioreactor, close it, shake it a bit, and open it after 2 days. This will work with glucose or so, but this will not work with oxygen, because this small oxygen is consumed within seconds in an aerobic process. So therefore I will need in aerobic processes, I always need to bring in the oxygen. So therefore, if I have a batch reactor, an aerobic reaction, it's not closed with respect to the gas phase. Otherwise, I will not have a very long reaction. So the maximum possible amount of oxygen must be transferred 10 to 15 times per minute. So it's, let's say this is the number one task, bring this oxygen in. So the driving force is very low. So because my concentration, my saturation concentration of oxygen is very low, therefore it's not easy, and the oxygen is often then the limiting factor. In order to achieve that, the complete reactor design, stereo design, and so on is tailored towards this oxygen transfer. You will see later on that you think always that stirring is that you to mix everything and to bring that you have an optimal transfer of your substrate to the cells, or bring the substrate away from the cells. But indeed, the design of the bioreactor is driven by bringing the oxygen into your reactor. So this is what is all the design about. So, and the side effect is of course that you optimize also the transfer of your substrate to the cell, but this is not the driving force of the design force. There you could use way lower stirrer powers just to achieve that. Now, the cellular oxygen demand, we don't have to forget that. We have one thing, we need to transfer the oxygen from the gas to the liquid, but at the end how much we need to transfer depends on how much is being consumed by the cells. So of course we shouldn't forget the cells if we talk about oxygen demand, because we should look at what do the cells actually need. The more they need, the more I need to transfer. So the cellular oxygen demand is nothing else than the rate of oxygen consumed by the cells, and that at the end this must be equal. That what you bring in is what you get out from the cells. Now the factors influencing the oxygen demand are quite straightforward. These are the cell species themselves, culture growth phase, the nature of the carbon source, and so on and so on. So also temperature can dictate that. So it's a specific growth rate is dependent on the temperature, and this then of course also dictates the transfer rate and so on. In batch cultures, the rate of oxygen uptake varies with time, so it's not constant overall. So first of all, the concentration of cells increased during the course of the batch, and of course the rate of oxygen transfer is a function of the specific rate of oxygen uptake fold the biomass. So of course if your biomass varies, the overall rate of oxygen uptake varies. So this is usually increasing, and therefore also this rate of oxygen uptake will increase. However, also the rate of oxygen consumption per cell itself, the specific rate, can change. Yeah. So and often in early stages it's higher. So if you look at curves describing that, you see that these are curves for 3 different organisms. These are bacterial cells, plant cells, and animal cells. So you see that in this Streptomyces, you have quite a steep increase in the specific rate of oxygen transfer. These are these squares here, and which goes down to later time points. So if your growth, this is your biomass concentration. So of course here you hardly have any growth. So this, you would expect that this is then going down, because without growth the demand is lower. But also in the exponential phase here you see you have variation in the oxygen transfer. By the way, this is not really exponential here, because this is a linear scale. So the exponential phase might be here. It's a linear growth. This is less pronounced, this difference in this plant cells here of the specific rate of oxygen transfer, but still it goes down. And the same is true for animal cell lines. So you see that the maximum oxygen uptake rate you have to achieve is not necessarily where you have the major amount of biomass. It's only true if you can consider the specific oxygen rate as constant, which is not the case. However, to estimate things, often things are nevertheless considered as being constant in order to have a chance to do. Now, if you compare these different systems here, the question is, where do you need to bring in the highest amount of oxygen per time if you look at this data here? Is it for Streptomyces, it's for Cantharus rosensis or plant cells, or for this animal cell lines? So please respond to that, and I will look in the chat in a second. Now I will first go back to the presentation and the next slide. Now, if I look at factors affecting the cell oxygen demand, of course the oxygen uptake depends on the biochemical nature of the cell and what nutrients I actually provide. So, for example, if I feed my cells on a highly reduced substrate like hydrocarbon compared to a carbohydrate, I assume that my oxygen demand will be higher if I have hydrocarbon, because it's more highly reduced. The interesting thing is that it's quite constant over a range of oxygen concentration. So it's also a function of oxygen concentration. However, below a critical concentration, the specific oxygen uptake rate drops dramatically. So as long as I'm over this critical concentration, I have a quite constant specific oxygen uptake rate. So my cells, the growth of these cells in this case is not oxygen limited. However, you have then a rapid drop below this value. So you need to ensure in your bioreactor to stay at concentrations which are in this range. It depends on the organism, but usually it's in the range of 5 to 10% of the saturation concentration. The higher you are there, the far away you're from this critical concentration, but the higher you are there at the saturation concentration, the lower is your driving force for the transfer from your gas phase into the liquid phase. So in reality, you will be somewhere here, but you need to be sure that you're higher than this value. And this is what you regulate in a bioreactor, what you will also see in the simulation in the lab course. Okay. Now, another thing which is affecting, of course, your oxygen transfer is the choice of the substrate. So if you use glucose, this is usually rapidly consumed, so the consumption rate of glucose is high, and therefore also the oxygen consumption rates are high. This is logical. If you use a substrate which is not as fast metabolized than glucose, you will also have a reduction in the rate of oxygen consumption. I already said that high degree of reduction will have a higher oxygen demand. So if you grow on hydrocarbons, you will are likely to have higher specific oxygen uptake rates, just based on the degree of reduction. But this is a more complex function, because of course you have also a rate of metabolization downstream, and usually the rate of metabolization of these hydrocarbons is then lower. So there is kind of a balance. So at the end, you would need to measure that experimentally in order to know it, or to look up the listed values. Okay, so let's have a look whether there are questions. So there is one suggestion that it's for plant cells. Yeah, so that's, we look back to the slide. Yeah, I forgot that there are not just questions, that there are answers. So you say it's for plant cells because you say at the beginning this O2 requirements are the highest. So Cave, you should have a look at the scales. Yeah, that's very important. So if you analyze this data, always check the scales. So you see, this is a specific rate per gram. Our specific rates are per gram, and specific oxygen uptake rate is per mole. Here it's per cell number. And so the units here are always different, what you see here. So you cannot compare directly the specific rates. But you see the oxygen uptake rate, Q0, that's the thing what you need to transfer at the end. This is always millimole per liter per hour. So these things you can directly compare, because there you have the same unit. And you see that here we go from 0 to 12, here we only go from 0 to 3, and here we go from 0 to 0.7. So at the end you need to look at what is the oxygen uptake rate, are these open circles. So the maximum here is round about 10 millimole per liter per hour. The maximum here is round about 2.5 millimoles per hour, and the maximum here is round about 0.6 millimole per hour. So you need the highest point is here. It's 10 versus 2.5 versus 0.6. So this is more than 20-fold higher than in animal cells, and is at least 3-4-fold higher than in plant cells. So this means that if you are in a bioreactor where you want to grow bacteria, you have the highest demands with respect to oxygen transfer. In a cell culture with animal cells, usually it's not such a problem to bring the oxygen in. However, you will see later on, usually one important factor in let's say enhancing the oxygen transfer, that's what we always also do in the lab course, is the stirrer power. And the bad news is that you need lower oxygen uptake, but at the same time you cannot stir as rigidly as with the bacterial cells in animal cells. So therefore you have a limitation. You will never reach these transfer rates you can reach for bacterial cells, because you are not allowed
to put the stirrer as rigid as for bacterial cells, because you will simply kill the cells then. And then your oxygen consumption rate will drop to 0. Yeah, that's the point. Okay, so that's the point here with respect to the curves. Now we go and have a look at the steps for oxygen transfer from a gas bubble to the cell. We said we have here the gas-liquid interface. We neglect everything which is from gas to this phase border, and we have then a diffusion through the liquid film here. And if we have an individual cell, we have then a transport in our liquid, and we have then a transfer into our individual cell. We don't talk about cell clumps here, so of course there it's not negligible. If we have then larger clumps, then we have cells inside, so of course there we have always diffusion. But for an individual cell, if we talk about an ideal submerged culture where we have all cells sitting individually there, we need to transfer then the oxygen particle through this liquid film around the cell, and within this phase we said we have convective transfer because we have stirring, complete stirring. However, now the cell is very small, so compared to a gas bubble. So this means if it's very, very small, this also means that the liquid film around the cell is very thin. And as it's very thin, again, the rate, the overall rate of the gas transfer from here inside of the gas bubble to inside of the individual cell is dictated by this liquid film around the gas bubble, and it's only marginally influenced by the liquid film around the individual cell. So we can neglect it. So at the end, we just need to have a look at this gas transfer here, which makes, of course, our life easier. So that's what I said. Just in written forms. Again, the rate limiting step is the diffusion through the liquid film around the gas bubble. And at steady state, the oxygen transfers from bubbles must of course be equal to rate of oxygen consumption. If we don't have a change in the oxygen concentration in our bioreactor, this in other words means that with growing cells in our bioreactor, this means that they consume the same amount of oxygen which is being transferred from the gas bubbles into the liquid phase. So we can simply put these equation in, and the equation 13 and 15 simply must be equal. Now, if we look at this equation, we can also say, we can derive what is actually the amount of oxygen which we need to transfer at maximum. So now we assume, we know that the Q0 is not, we have talked about that, it's not constant. But nevertheless, we can estimate it. We can say if our Q0, we take a value which is closer to the maximum value, and we want to estimate what is our maximal demand here on this side, which is of course our Q0 fold the biomass concentration, what we can achieve. So if we say Q0 is constant, we can calculate how high we can go with our biomass concentration if we have a fixed KLa value. In other words, if I have a certain bioreactor which can at maximum achieve a certain transfer given by this KLa, then I can calculate what biomass concentration can I achieve in this system, simply by, in this case, X max is then simply this term here divided by Q0. So I say I have measured my KLa using, for example, the methods you do in the lab course, in the simulation. I have measured the KLa, and I see I can achieve a KLa of 0.25 per second at maximum. More, it's not possible. So I have this value then. I have then my Q0, which I need to pick up from tabulated values or so. And then I just need to have an idea of this term. When does it get maximum? Well, maximum is, of course, if this value here is 0. So this is the solubility of my oxygen in the liquid. And if this value is 0, I cannot get higher with the driving force. So this, at the end, is my maximum, so-called maximal supported
cell density. And that's very important because up to this cell density I can go in a real exponential growth. At higher densities I can still grow my cells to higher densities. However, then the oxygen transfer rate gets limiting. And this is what you have already always seen in your shaking cultures. Usually people, if they measure growth curves, shake a bit and think everything is fine. But these are people who have no idea from bioprocess engineering. These are pure microbiologists, because it's very soon that even if you have medium cell densities, the transfer already gets limiting, and then you have no more exponential growth. You have a linear growth. And this is only what you see, as you remember, if you watch an Allen transform presentation where you plot your Allen transform biomass versus time. You remember that when we talked about growth. Okay, so the maximum supported cell concentration is simply by putting the CL0 and solving it to the biomass. Then we get this term. Very important term, because then we have an idea how high we can go with our cell concentration at a certain, with a given KLa value. I can also, at the other side, I say I want to have a certain cell concentration. My requirement is to get a certain cell concentration. I have my Q0, and I can say now I calculate what is my KLa value I have to minimally reach in order to still support this growth. So you can do two things. You can first of all look at what is the maximum biomass concentration if I have my given KLa, or you can say I need to go to a certain biomass concentration. I know that I have this critical oxygen concentration in my liquid. So what is the KLa I need to achieve in my system? And then you can optimize your system in order to see whether you get to this KLa. And now we come to an example. Now we have talked for hours, and now we come to an example. So we have a strain of Azotobacter, which is cultured in a 50 meter cube stirred fermenter for alginate production. And KLa is 0.17 per second, and the solubility of oxygen is approximately 8 times 10 to the minus 3 kilograms per meter cube. Now this is the specific rate of oxygen uptake. It's 12.5 millimoles per grams per hour. What is the maximum cell concentration supported by oxygen transfer in the fermenter? And B, now we have a growth inhibition after we have added copper sulfate accidentally, and this causes a reduction of the specific uptake rate from where I have it 12.5 millimoles per grams per hour to 3 millimoles per gram per hour. What is now the maximum cell concentration which can be supported? And what we do is we calculate now the part A, and your job at home is calculate part B. 0.5 points, and you will see that these are easily, let's say, easily gained 0.5 points. Let's start with the equation we need. So you remember we are talking about, we want to calculate here the maximum supported cell concentration. So in other words, we use this equation, X max is equal to KLa fold C star divided by Q0. This is the equation we're talking about. And now we just need to look at the values here. Q0 is 12.5 millimole per grams hour. Our C star is where are we? 8 times 10 to the minus 3 kilograms per meter cube. KLa is 0.17 per second. Then we need to convert everything to units which are similar. So I would usually we use grams and liters. So converting this is we start with this one, which is simple. So we just convert the kilograms into grams, so this is straightforward. 1000 gram is 1 kilogram, and this then kicks out our kilogram, meter cube, and liters. And now I can shorten out my meter cube. By the way, I can now also shorten out my 1000, so it's the same 8 times 10 to the minus 3 grams per liter, and I have 8 to the minus 10 to the minus 3 kilograms per meter cube. Just check it always to be sure that things are correct. Now I need to convert this one, so I first convert the millimoles into moles. So 1 mole is 1000 millimole, and I have now get rid of the mole, and of course my oxygen concentration is 32 grams per mole. Now I am in grams, and I need to convert the hours into seconds. So 1 hour is 3600 seconds. Check, check. And this is already grams. So if I put everything in the pocket calculator, just try it yourself. It's 1.1 times 1.11 times 10 to the minus 4 grams per gram per second. So the conversion here is the secret. And again, always do it like that. Please get used to doing like that, because you reduce the errors. And for the exam, it's important. You could also do, of course, the conversion directly in the equation. So you could put everything and do the conversion in the equation. But it's in 99% of cases, some errors happen. And if you then have an error in the conversion in the equation, and you just come up with an end result, which is then of course also wrong, I cannot give you a point for that, because the result is wrong, and I cannot attribute it in points in between. So if your conversion is wrong, and then you put the wrong value of the conversion into your formula, and the result with your wrong conversion is correct, you will get a point for this calculation. You will get a point for this calculation, but of course no point for this calculation. So then it's fine. But if you do it in one, I cannot give you subpoints, you will lose that. So make sure that you do the conversion extra, but only convert what you need. Do it that you have the least conversions to be done. In other words, for the Xmax, we just put it now in the formula. Xmax is equal to the KLA, it's here 0.17 per second. And then it's fold the solubility. It's 8 times 10 to the minus 3 grams per liter divided by, and now we come with our Q0, which is 1.11 times 10 to the minus 4 grams per second. And now, of course, everything hopefully should shorten out. So now we shorten out these grams, the seconds, and we end up with, we put that in our pocket calculator, 12.3 grams per liter. So this is a biomass concentration which looks reasonable. If you end up with biomass concentrations in the range of tons per liter or way lower, then this looks unreasonable. This is the result here. So the question was, what is the maximum cell concentration supported by oxygen transfer in the fermenter? It is response 12.3 grams per liter, and you do the same if you change the oxygen uptake rate to 3 millimoles per grams per hour. But let's have a look whether there are questions. For plants as Cl is the concentration in the liquid phase, right? Yes. Cl is the concentration of O2 in the liquid phase. Here you don't have Cl because we look at the maximum concentration. Wouldn't G get cancelled in Q0? The grams. Okay. So you want to know whether the grams get cancelled. You can take this grams out. I would never do that. We talk about gram oxygen and gram biomass because these grams are different. So keep this grams inside. It's not gram oxygen per gram oxygen, it's gram oxygen per gram biomass. Keep it. Yeah. But we shorten it out then here, because what we shorten out, by the way, is here this gram oxygen with this gram oxygen, and we stay with the gram biomass. So it would be
the ideal thing would be to keep this gram biomass here, to make this as an index, gram oxygen here, that you see this gram is different from this gram, and then you end up with the correct value. Okay. Yeah. I would say that's it for today. Thanks for your attention. Thank you for being here, because we don't have a lecture today officially, so it's an unofficial lecture. So this maybe next time that I do the unofficial lectures without a face. So we'll see again in a week. Again, I said that this lecture then is just on just a video. With respect to the presentation in biomedical engineering, I already told you that there we will you need to put your face in, that's clear, and I will most likely make up a video. So thanks again for your for being here with me, and now enjoy Pfingsten. Yeah? So for whatever religion you belong to, enjoy the holidays. Thanks again.